Welcome back. Let's dig a little deeper. What does the Node.js runtime over here include beyond just the V8 engine? What do the internals of Node look like so we can better understand what's going on behind the scenes? Remember, V8 here is what lets Node run JavaScript. But there's so much more to Node than just the ability to run pure JavaScript. There's this entire environment, this entire runtime that runs outside the browser, that lets us do things that aren't part of the JavaScript programming language out of the box. If we run JavaScript code like 2+2 or concatenating two strings like woohoo, in Node, V8 will know exactly how to execute that code and give us the result on our computer. But what happens when we try to get the arguments passed to our Node process? Or when we try to read and write files on our system here? All these things that Node can do that our browser can't. For that, let's take a look inside of the Node.js runtime. We've already seen that we have the V8 engine, which is what allows us to run basic JavaScript code like 2+2. But also part of Node are our Node.js APIs, or additional functions that allow us to do things like talk to the file system to read files, and make HTTP requests, or look up paths on our computer for files that we might want to read and write. And even things like the crypto functionality, which has some built-in code that allows us to make our Node programs more secure. For example, by encrypting some data for us. Now, when V8 sees some code that uses these features, it'll say, okay, I need some help to execute this. And it'll call the corresponding functionality in our Node.js APIs. Some of this is written in JavaScript, but also in lower-level languages. Languages that are more like the machine code that the hardware on your computer speaks, like C and C++. And that's where these Node.js bindings come in. These bindings are what lets your JavaScript code call functionality that's implemented in C and C++, which have things like really highly optimized and tested code to encrypt your data, or to make calls to your file system, reading and writing files regardless of which operating system you're on. So for much of their functionality, the Node APIs will call into these C++ Node.js bindings. Now, the actual implementation of some of this core functionality, like working with files or the HTTP protocol, lives in what we call libuv, with this fantastical creature over here as its logo. libuv and V8 are the two most important internal components of Node.js. That's because libuv deals with input and output tasks. It's this highly optimized library of code written in the C programming language that deals with input-output tasks that Node can delegate to other parts of your operating system. This is like your boss telling you to create a 5-page report on the strengths of Node.js, where he's delegating that task to you. Probably because he knows you have the time and expertise to do it. Just like that boss, What this means for Node.js is that, say you're downloading a web page, and that download request takes 30 seconds. Well, a download request is input that's asking for output, for a response from the web server. So what's going to happen is we'll make a request in JavaScript using the HTTP module, a function from this HTTP Node.js API, and through the Node.js bindings, Node will pass that task on to libuv, which will just tell your operating system, okay, here are the things that I need, say the contents of a web page, and the operating system will go off and perform those tasks. So we've delegated that task to the operating system, and our Node program, our JavaScript, doesn't have to wait around for the response. Node just says, okay, operating system, let me know when my task is complete, and I'll get right back on it as soon as I can. This is called asynchronous I/O, or asynchronous input-output. It's what Node is best at, and it's something that we're going to learn a lot more about in the next coming videos, because it's so important. Nearly all of the code that we write in Node involves some form of asynchronous I/O. This includes functionality provided by libuv, like working with your file system and making requests over the network, over the internet. Whether you're on Windows, Mac OS, or Linux. You see, part of the challenge of working with all of these different operating systems, particularly when you're working with lower level languages like C and C++, is that each of them accomplishes the same thing differently. The way you open a file on Windows versus Mac OS is actually quite different, even though you're accomplishing the same thing at the end of the day. And that's where the beauty of libuv shines. It abstracts away all of these specific ways of reading a file, for example, so that Node will work on any system, on any platform. It does this by implementing the functionality in libuv and exposing it to this higher level layer, which is then translated back to our JavaScript. Using what we've just learned, we can adjust our bird's eye view of what Node does, replacing our old model with a new, more accurate model, where our JavaScript goes into this Node.js process, not just with V8, but with the additional components we just talked about, which process our input and send it back to the user to do something. All right, so we have this diagram in front of us. We've talked about things like implementation and bindings. But what exactly this means for us and how each piece connects to each other probably doesn't seem fully clear to you yet. We've been talking about the internals of Node, but let's actually apply this theory. That way we can better understand these deep internal workings of Node. For that, I'll see you in the next video. Welcome back. We've been talking about how the internals of Node are structured. Now it's time to look at the code behind Node.js. As a quick recap, we saw that our JavaScript code executed in V8 will sometimes make use of these built-in Node.js APIs. And when we call one of the functions in these APIs, they go through the Node.js bindings and handled by libuv in some way. So let's explore exactly what's going on when our code goes through the flow we see here. The Node.js project is hosted on GitHub, and you can browse it by going to github.com/nodejs/node. What we have here is the actual code that makes up Node, that has enabled us developers to create all these amazing projects and websites. Things like Netflix and projects at NASA are powered by this source code. Isn't that cool? Because Node and its components are open source, we can actually look around this code and figure out how it works. Learn why things are done the way they are, and even potentially contribute new features. If you find a crazy bug that no one else has experienced, you're able to submit a fix directly to the repository here and contribute to something that has actually changed the internet. Okay, diving in, we have a few folders in the Node.js project. The two that are most interesting to us are the lib folder and the src folder. Lib over here has the JavaScript side of our Node APIs. Each module in our Node.js documentation. Remember how we had access to all these globals and APIs that Node provides for us, like the console object, HTTP, a module to get information about our operating system and access paths on our hard drive, or to get information about the process and the arguments that were passed into Node. Each of these has a corresponding file in our lib folder. We can see that there are a few folders here, but scrolling further down, we have all of these files for each of our APIs. Console. We have the file system and HTTP, all the way down to our process. Each of these files defines the functions in our documentation that make up the Node APIs. That's the lib folder. The other folder of note is src, which is the C++ side, with our low-level Node API bindings. It's that connection between the JavaScript world and the C++ world. Let's look at an example. Say we want to open a file. We know it's part of the file system module. And if we look at the documentation, scrolling down here, we'll see a fs.open function right here. This lets us pass in a path and some additional arguments. But where does this live? What's it actually doing? How does it work on both Windows and Mac OS? Well, we can investigate in our source code. We know in the lib folder, there's going to need to be a file for our fs module, because that's the module that open is part of. So we'll go into our fs.js file here, and because it has over 2,000 lines, I'm going to do a search for the open function. And I can see that one of the results is a JavaScript function, where we can follow along with the logic. We can see that we're validating the path as the first step. And then, depending on what the arguments are, we do a few different branches. There's some different options. But the most interesting piece here is this function right here, binding.open. This is where our Node.js internal bindings come in. This function will convert the values between JavaScript in our FS module and C++ over here, allowing Node to call into that optimized lower level C++ code. So we're calling the open function available in our bindings. We can now see the full implementation of this function by going to that src folder. And again, I have some folders here, but scrolling down all the way to node underscore, I'll have a node underscore file.cc over here, where cc is one of two most common file extensions for the C++ programming language. Just like we have .js for JavaScript and .py for Python. The other extension you might see for C++ is .cpp, while the H file has the headers. Usually we'll want to look into the cc file for the bulk of the code. So going into our node file.cc, we see this C++ code. And again, this file is going to have thousands of lines of code. That might look a little bit scary if you haven't done C++ before. But we don't need to know C++ to learn something from this. If I scroll all the way to the bottom of this file, and then go back up slightly, I will find this initialize function and a bunch of these set method calls. These are associating functions from JavaScript with C++ functions in this file. So remember, we were calling fs.open, which is going to call the open function with this capital O in this file. So I'll do a search for that. And one of the results is the C++ implementation of our open function. Check it out. We can look through this code and see that it's doing some validation on our arguments. But the interesting bit here is we'll see this uv_fs_open being referenced in an async call and also in a sync call. This uv_fs_open is actually a function inside of libuv that we're saying can be asynchronous or synchronous. And exactly what the difference is between synchronous and asynchronous calls is actually a really interesting topic that we'll be going into as well. But what we can learn from this example here is that things that start with uv_ are references to libuv. And if I do a search for that in this file, you can see there's quite a few places that libuv is being used. All right. This is getting a bit deep. How far does the rabbit hole go? Where is our open functionality actually implemented? Let's complete this deep dive into the internals of Node by going all the way into the libuv source code. After this, you'll be able to say you went from the highest level JavaScript to the lowest level internal workings of Node. This is something to be proud of. Not many people can say they've done this. So on that note, I'll see you in the next video. Welcome back. Let's complete this deep dive into the internals of Node by going all the way into the libuv source code. We're about to venture somewhere that very few Node developers ever go. So we're going to have that extra advantage when it comes to knowing exactly what Node is doing. So let's get into it. In our browser, we can go to libuv.org, the official site of our favorite library over here. While libuv is part of Node, it's also meaningful on its own. Remember, Node allows us to use libuv by connecting to it with the Node.js bindings, which allow the functionality in libuv to be used by our JavaScript. But other programming languages have bindings to libuv as well. We can see this if we go to this documentation tab and follow this others link here. We can see, scrolling down all the way to the bottom here under bindings, that libuv has bindings to Ruby, Lua, C++, and Python, and all of these other common and less common programming languages. These are all client languages that can use the libuv library, just like Node. This is why it has its own website, which you can see is made with love by the libuv team. Node is libuv with a very well-known client language. That's JavaScript. But as we just saw, libuv has bindings to other languages as well. So the libuv code lives in a slightly different place, in a different repository. And let's just get into it. Show me the libuv code. We're taken to GitHub under the libuv organization. And again, we have a few folders that we can explore, containing our documentation and tests. But the bulk of the C code that makes up libuv is in this source folder. Now remember, we're exploring what happens from the JavaScript to our final result when we run fs.open to open a file. We've seen the call through the Node.js APIs in our fs.js file and going through the Node.js bindings. Now let's find it in libuv. Now, in our source folder, we can see that there are two main folders. One for Unix, which is a family of operating systems that includes both Linux and macOS, where things tend to work in similar ways. This is because both Linux and macOS are descendants of this original Unix operating system. Windows is also a family or a group of operating systems where things tend to work similarly. There are incremental updates with each version, but many of the fundamentals remain the same. So it makes sense to group these together. Let's start by looking at the implementation of fs.open on Unix. Scrolling down in the folder, we can see references to Unix systems like Android, which is Linux-based, and Darwin, which refers to macOS. Darwin is the code name for the core components of the Apple operating systems. So we're on the right track, but the open functionality is going to be in this fs.c file. Notice that unlike the Node API bindings, libuv is using C rather than C++ with its .cc file extension. Going into our file, we see that we have another few thousand lines of code. And we scroll down, we can see that this is C code, which might not really mean anything to us. But remember, the API bindings, we're calling this function inside of libuv, and we can do a search for that function, which, if you remember, was called uv underscore because it's in libuv, and then fs underscore open. This function is being called in a few places, but let's look for the definition. So our result over here is this C function definition. But this doesn't seem to be doing any opening of files. It's just really calling this init and passing in open. This is a way of calling functions that libuv uses, but the good news is that we don't have to search far for the actual implementation. The actual implementation is in this function called uv underscore underscore fs underscore open. All right, here we go. This is where the hard work of actually opening the file and calling down into the operating system and doing file system operations is done. When we call this open function here, this is the actual open function for Unix operating systems. That makes a system call down into your operating system to do whatever it needs and then give you a handle on that file, a way of working with that file and reading and writing to it. That's the R that we get back from this function call. And it's transformed and returned all the way back up into our JavaScript. Wait a second. Let's go to our Windows version now. So we want to go back out of our Unix folder and into our Win folder, where we're going to have another fs.c file. Notice there's fewer files here for other variants of Windows because Windows operating systems are all relatively similar. There's not as much variation as between Android mobile phones and macOS on Apple computers, and these open source distributions of Linux that there's hundreds of. So Windows is simpler in some way, but let's see what this fs.c file has in store for us. Now remember, we're still looking for uv underscore fs underscore open. That's what's being called from our Node.js API bindings. And again, we have this init pattern, where the actual function that opens the file lives close by. And we can find it by doing a search for other functions that look like open. So we just saw one. And then the second one is this fs underscore underscore open function. This is where the good stuff happens on Windows. And we see these D words, which are structures that Windows uses. Scrolling down, we can see that this function is actually a fair bit longer than the Unix one. It's actually well over 100 lines of code, maybe 200 or 300. And we only get to the actual call that opens the file on Windows all the way down here. This create file W function gives us that file handle that we just talked about on Windows. And there's more after that. This open_OSF handle function over here transfers ownership of the file handle that we got from create file W to this fd variable here, or our file descriptor, which is what we then use in C to work directly on the file. And finally, at the bottom of this super long function, we set a result with that file descriptor and return it back up through our code. So why is this function so much longer than the Unix version? Well, for one, things are just a little bit more involved in Windows land. But there's also a bit of code here near the beginning of our function that allows the results of opening a file to be compatible between Windows and Unix, so that we can work with files in the same way, regardless of which operating system we're on. This is one of the benefits that working with libuv gives us as Node developers. Okay, so maybe you've been following along so far, but now you're wondering, will I need to know C and C++ for this course to be a Node developer? The answer to that is a resounding no. The whole reason why we have high-level languages like JavaScript and runtimes like Node is so we don't have to write code in these low-level languages and worry about all of these complications that you've had a taste for here. But as we learn more about what Node does, having this knowledge will allow us to be not quite as intimidated by the internals. We've now explored this code as far as we can. Any deeper and we'd have to start looking at the C libraries and the operating system code for Windows and Linux, for example. Now we can point out how things are implemented in the underlying Node source code. This is where our fs.open function call journey ends. We did it. Going this deep is not something that many people can do. So consider yourself ahead of the game. Let's take a well-deserved break, and I'll see you in the next one. Bye-bye. All right. That was quite the journey into Node's deep internals. Now that we've come up from our deep dive and are back on land, we're going to take things step by step. For the first step, let's get one definition straight. Throughout the course, and especially in this section, you'll hear the term asynchronous come up again and again. What does asynchronous mean? In programming, asynchronous is often described as the opposite of synchronous, where synchronous means code that runs line by line in sequence. So asynchronous code is code that doesn't necessarily run line by line. Let's put aside programming for a second and look at an example. Say we have a list of things that we want to do, some goals that we want to achieve on our way to being the best developer we can be. Maybe we want to start by learning HTML, and our plan is to then learn JavaScript and move on to Node, eventually getting hired at our dream job. If we're doing things synchronously, what we'll do is we'll learn HTML as best as we can, and only after learning everything we think we can possibly learn and ticking that box off, do we start learning JavaScript. And when we think we've become the best possible JavaScript developer we could possibly become, we check that off and move on to Node. And so on until we achieve that goal of getting hired. This is a synchronous way of completing our tasks. We go through our goals one by one and only move on to the next goal when we're completely done with the previous one. In contrast to this, with the asynchronous approach, we could learn HTML really, really well, as best as we can, and then we start learning JavaScript. At some point, we decide we're comfortable enough with JavaScript as a language and move on to Node. But then, along the way, we work really, really hard, have some job interviews, and hey, we get that job that we've always been dreaming about. But we're still learning JavaScript and getting better. And we're still learning Node. These are skills that we constantly improve even after we've gotten hired. I know I'm still learning even after working with Node for years and years. In real life, we tend to achieve our goals asynchronously. We're getting better at Node, but while we're doing that, we're also getting better at JavaScript. Well, code works in the same way. For most tasks in our programs, it's possible for our computers, our machines, to work on multiple tasks at the same time. When one piece of code is still executing, but your program is already moving on to the next piece of code, that's asynchronous code. Oftentimes, in your programs, there will be some asynchronous functions. These asynchronous functions run in the background while your JavaScript has already moved on to the next line of code. This can be super useful because, for example, if your program is a web browser and it needs to spend some time loading a page, maybe my search results, to find out more about the Pacific Ocean. We want the browser to do that in the background, don't we? We want our browser to still be able to handle our button clicks and to let us load other web pages, even if something is loading in the background. Maybe I'm searching for images of mountains. Asynchronous programming is what allows us to do all this, handling many things side by side. And that's something that Node.js is really good at. We'll keep learning in the next video. I'll see you soon. Hello again. Let's get something straight. Something that's important for the rest of this course, the rest of our careers as Node developers, and even as JavaScript developers as a whole. What could be so important? Well, it's this part here. That Node.js is an asynchronous, event-driven JavaScript runtime. We've been hearing about how Node is asynchronous and that it's really good at working with asynchronous tasks. So what exactly are we talking about here? Let's find out. To demonstrate, let's set up a race in this race.js file. So we're going to see who's quicker. Going into my emoji database over here, we're going to have this rabbit taking part in our race. So we're going to say console.log and have the rabbit finishing. And the little rabbit is going to be racing against this slow turtle over here. So we're going to have the turtle finishing right after the rabbit. This is what we call synchronous code, where synchronous just means that the code executes line by line in order, waiting for the previous line to finish before moving on to the next. So the output of this program should be fairly easy to predict. If we pass in race.js to Node, we get, oops, I'm running the file from the wrong folder here, so I need to change directory in my terminal here to my desktop. And now I can run node race.js and hopefully see my predictable output, where the rabbit finishes first because her line of code here came first. Okay, I hear you saying that this is really basic stuff. So let's compare this with the asynchronous approach. You might remember a function from our Node globals, or maybe even from the browser and the window object, called setTimeout. This function allows us to set a piece of code to be run at a later time. And the way we do that is by passing a function as the first argument here. So we can use this anonymous function using our arrow syntax. Or we could use our function keyword here. That would work just as well. And have the rabbit finishing inside of that function. So this function represents what's going to execute. And the second argument is the timeout. So that's how long Node will wait before attempting to execute this function. So let's just say 1,000 milliseconds or 1 second. Our line of code here is now asynchronous. And the function that we're passing in to be executed at a later time is called a callback function. Callbacks allow us to say, when you're done doing all of this work, call me back and run my code. These callbacks are executed when some event occurs. With setTimeout, it's just after waiting for a certain amount of time. But other asynchronous functions will wait for a file to be read or a request against a database to complete. Maybe a user is logging in. All of these things that can take some time to complete, that we'd otherwise be waiting around for. This is why callback functions are at the foundation of Node. They allow us to build web servers that can handle thousands of requests all at the same time, without waiting for the previous one to complete first. So can you predict the output of running this program? Maybe after our discussion, it seems obvious to you. But we've just introduced a really powerful concept. Now the slow little turtle here finishes before the rabbit, even though the code for the rabbit finishing came first. This out-of-order execution is something that can take some getting used to. Our code is still running line by line, but it doesn't pause for the asynchronous function. Instead, setTimeout immediately returns, our turtle finishes, and then at a later time, after this timer expiring in the background, our callback function is executed. This is powerful stuff, so make sure it makes sense to you, because we're going to be seeing a lot more of these asynchronous functions and callbacks throughout the course. And we don't want to get caught off guard by a slow turtle winning the race unexpectedly. On that note, I'll see you in the next video. Welcome back. What is a non-blocking function? Well, blocking code executes synchronously. Both Node and your browser have a built-in JSON.stringify function that blocks until completion, and any commands after it only execute once it's done doing what it does, which is that it takes a JavaScript object and returns the string representation of that object, telling us that food is love. But our non-blocking functions, like setTimeout, execute in the background or even in parallel with the rest of our code. The 1-second timer is running while the next line of code is already executing, and the myFunction callback might run in parallel with another piece of code. Like, for example, making a request to google.com. When we have some code like our setTimeout, or we're making a request, or even reading a file on our computer, you might think that your computer, your CPU, which is what is running your JavaScript code, is working really hard to read that file or to make that request against Google servers. This is not the truth. Your CPU is deceiving you. What's actually happening is that your CPU is passing off or delegating this work to other devices on your computer, like your network card, which handles communication with other devices on the internet, or your hard disk, which is searching for that file and reading the bytes that it's composed of. While these devices are doing their hard work, your CPU is basically just waiting around or going off to do some other work. It's our non-blocking asynchronous code that allows our CPU over here to continue executing the other instructions in our JavaScript program, while we're making use of our other devices, like our hard drive. We can make more efficient use of our CPU. So what's the lesson from all this? Our stringify function might not normally take very long to complete. But imagine if setTimeout was a blocking function, or make requests. These functions that can take a very long time to complete are the ones that we want to be careful with. We want to make sure that our long-running functions that are waiting for input and output from our devices, like our hard drive, are non-blocking, allowing Node to continue executing other code, and making sure that that CPU of ours stays awake. All right, I'll see you in the next one. Here's a question for you. Based on what you've seen so far, is JavaScript synchronous or asynchronous? This is a common job interview question if you're going to get hired as a Node developer. And it's something that's key to understanding Node and JavaScript fundamentals. So consider this good practice. Think about this for a second. Is JavaScript synchronous or asynchronous? When you're ready, let's continue with this video. Okay, have you figured out the answer? Out of the box, JavaScript is a synchronous language. One statement executes after the other. However, we've seen that we can write asynchronous code, where we are able to execute a callback function in the future when something completes. What's up with that? When JavaScript is run in certain environments, like your browser or Node.js, it allows us to write asynchronous functionality. But this functionality, like setTimeout, isn't strictly part of JavaScript. It comes from our Node APIs, from our global object, or in the browser from our window object. setTimeout is clearly an asynchronous function, but it only works thanks to libuv, thanks to functionality that is not part of the core JavaScript language. So JavaScript can behave in an asynchronous way, but it doesn't come this way out of the box. You have to manipulate it to be this way. So what is Node doing to make setTimeout and our other asynchronous functions work when JavaScript itself is a synchronous programming language? Let's learn more so that we can feel comfortable discussing this in a job interview setting. I'll see you in the next one. We've reached a big question. Is Node.js multi-threaded? Chances are you're well aware that computers with more processors and processor cores are more powerful, more expensive, and generally more desirable. And the way that we take advantage of our multiple cores to run our programs faster is by using threads. But what exactly are threads? And how do they help us? Let's look back at our node diagram. What we have here is a series of internal components of the Node.js process, and how a function call like fs.open might flow through these internal components. Well, the Node.js process, like any process on your computer, represents a program being currently executed. In this case, the Node.js executable. I want to show you a diagram that will help put things together from how exactly the Node process runs on your operating system to how your CPU allows you to run code asynchronously. We start from processes. What happens when you run a process on your machine? Anything like the Chrome browser or the Node process. Well, processes are containers containing your code, which lives in the memory of that process. So we might have some code with a few functions, like a first function that calls this second function, and the second function just returns the number 42. And then below, we have this code which creates a new thread using the code from that first function, and then creates another thread using that same function. Now, this is pseudocode. It's not code in any real programming language, but it's a lot like the code that you might see in a multi-threaded programming language. Something like Java or the C++ programming language. So the idea here is to have two threads, both running the first function in parallel, asynchronously. These two lines of code here might remind you of something that we saw recently, which is the setTimeout function, right? We're passing in a function to be executed asynchronously, and we're just not passing in a timer. We're saying, hey, CPU, start this thread as soon as possible. And so what happens is when this first line of code is executed, our process creates a new thread, which also lives inside the memory for our process, and it represents a single sequence of operations. Operations like functions, and the function calls that are contained in the code of your process. This sequence of operations lives inside the call stack, which is in turn part of the thread. Like a stack of bricks, new function calls go on top of the stack, and functions that are done executing are removed from the top. So in our first thread here, we start with the first function, which is added to the top of our empty stack. And then the first function calls the second function, which gets added to the stack. And if second function made any other calls, they would be continuously added on in sequence. Now, when second function returns the value 42, the second function is removed from the top of the stack. The return value is sent back to first function, and the first function is now completed, so it's removed from the top of the stack. Now, that's if we had one thread. But remember, we're creating two threads here. So what would happen in this code is we would first create that new thread, but then we would do the same thing again. We would create a second thread with its own call stack. And these two threads would run asynchronously. So in thread 1, for example, we might go through the same flow that we saw previously. We might call first function, call second function, and so on. And then perhaps thread 2 finishes calling first function and is ready for the rest of our code for second function. Notice that the two threads don't have to be in the same place in our code, in the same state. In fact, thread 2 might even be executing a different function altogether. So it might call second function directly, or even a third unrelated function. The point is, we have processes and threads inside of them, and they share memory and code, but not call stacks. Your threads can execute side by side if you have more than one, each running part of the code of your process. And that CPU of ours can constantly switch back and forth from one thread to the other to simulate executing them in parallel. But more importantly, if we have multiple cores in our CPU, each core can be dedicated to executing one thread. This applies to all processes. Your operating system can have threads helping it run things side by side. Your code editor, like VS Code, can have threads. And even the browser you're currently watching this video on has multiple threads, helping it run smoothly. So back to our example. How does this process finish? Well, the second thread needs to complete the code that it's running. So the second function gets added to the top of the call stack. And then maybe the return value of our second function is returned back to the first function in the first thread. So it gets removed from the call stack, and that thread completes. And then the same thing happens on thread 2. The important thing to note here is that the two threads are independent of each other. In terms of executing the code, they can both be in any spot of the code depending on when they were created and how fast the operations they're executing completed. Maybe even what other threads and processes were running on your CPU. All of these things can affect which thread completes first. So threads execute side by side, allowing us to execute code asynchronously by putting it on a new thread. This sounds great, but traditionally, for your application to have threads and to take advantage of everything we've talked about in this video, the programming language that your code was written in needed to support multi-threaded programming and the creation of new threads. But the reality is that things aren't as simple as they look here. Multi-threaded programming is a difficult concept to master, especially in languages like C++ and Java, where you need to have an understanding of things like mutual exclusivity and locks. These are mechanisms to keep your code and the data inside the code synchronized between all the threads so that they can work together towards a common objective. Doing this effectively can be extremely complicated to reason about and understand, and to debug when something goes wrong. You'll run into issues like what's called a deadlock, where two threads are stuck, waiting for an action that can never actually occur. Believe it or not, avoiding deadlocks is something that experienced programmers struggle with when working with these multi-threaded programming languages. It's really not an easy job. It's a source of huge bugs in basically all multi-threaded software. And sometimes you just don't want to deal with all of this multi-threading. So that's the decision that Brandon Eich made when he created JavaScript. In JavaScript, we don't have to worry about multi-threaded programming and all those complicated concepts like deadlocks, because we can't. Traditionally, JavaScript is a single-threaded programming language. If you've already been working with JavaScript for a little while, answer me this. When's the last time you had to deal with deadlocks? Most likely the answer to this is never. JavaScript simplifies things by only allowing one thread to execute your code at a time. So then, how is Node allowing us to open files and make HTTP requests asynchronously? Does Node introduce threads into JavaScript? Okay, using our newfound knowledge on processes and threads, let's answer the original question. Is Node.js multi-threaded? But first, let's take a quick break. I'll see you in the next video. Welcome back. Here we go. The thing that allowed Node to be so successful is the ability to run JavaScript code asynchronously, and doing this in such a way that developers like you and I could focus on our application and solving interesting problems rather than worrying about complicated multi-threading logic. We've learned that JavaScript is a single-threaded language. So if it's not threads, then how does Node allow us to execute code asynchronously? Does Node add threads to JavaScript and just do a really good job of hiding them? Well, Node executes JavaScript code, so it has to follow how the language works in being single-threaded. In Node, we have one main thread. This one thread runs the V8 engine, our JavaScript code, including the Node APIs, as well as a super important part of libuv, which is the event loop. We'll get to the event loop in a moment, but a blocking function in any of these components will cause our JavaScript to block, halting execution of our program until that blocking function completes, which is not great. But that's not the whole story. For a complete picture, we need to take a better look at our favorite library, libuv. We've seen that libuv handles our input-output functionality. Specifically, libuv handles the two main types of I/O. File system operations, like the functions in our FS module, as well as the other most common form of I/O, which is network operations. We're able to execute all of these functions asynchronously thanks to this event loop. This event loop is code in libuv that runs our asynchronous functions and executes the corresponding callback when the result of the function is ready. In Node, anytime we call an asynchronous function from JavaScript, it gets put on that event loop. This applies to our asynchronous network and file system operations. So all of our JavaScript code is running on the main thread, and any asynchronous functions are put on the event loop, which then goes off and tells your operating system to run the asynchronous function, notifying the event loop when the result is ready. It's kind of like your boss deciding when your code executes and getting notified when the work is complete. It continually listens for new events and delegates this work that we don't want blocking our main thread. Now, where does the work that gets put on the event loop actually get completed? Who are the employees or the workers that help the event loop get things done? There are two main options. Some tasks, things that tend to involve the network, like talking to servers over the internet, are done directly in your operating system, while other tasks, like reading a file, are done in what's called the thread pool. Let me explain. Inside of libuv, we have this pool of threads, or in other words, a group or a collection of threads, which are set up ahead of time and are available to take on work as it comes in. Remember, libuv is written in the C programming language, which does have threads. So our thread pool takes advantage of that. The threads in our thread pool are just like the threads in our process. There's one for the main thread that's executing V8, as well as the event loop, and there's a few threads, 4 by default, that are ready and waiting in our thread pool, with each of them able to handle one task at a time. We have a limited set of these threads that are available to take on work that are reused throughout the life cycle of our Node.js program. This saves our CPU from doing the additional work of creating and destroying new threads for every task that comes in. If we run out of available threads on our thread pool, well, we just have to wait for a task to complete before our thread pool is available again. So how does everything fit together? For file system operations, which use the thread pool, libuv would send the work to one of the threads, where it would run through what it needs to do, independently of all the other threads in our application, including the main thread, which is running our JavaScript code. So this would happen in the background, and when the operation completes, the event loop would get notified of the result, executing the corresponding callback and making sure that our application is running smoothly. But there's something worth noting. Only some operations use this thread pool. There's a common misconception, even with experienced Node developers, that all asynchronous functions are executed in the thread pool. Node actively tries to avoid this because, well, threads are more complex and use up the limited resources of our thread pool. Instead, where possible, libuv uses the operating system directly, specifically the operating system kernel, which is the core part of the operating system that talks to the computer's hardware and has multiple threads of its own. The kernel is really good at doing these basic operations, like talking to other computers over the network, using its own capabilities. Whenever the right functionality already exists in your operating system, libuv will just make the appropriate call, saving us from using the valuable resources of our thread pool. And so, for most asynchronous operations, we skip over this thread pool. When our operation finishes running in the operating system, the events loop will receive the signal and execute any callback functions. All of this is what allows the Node.js environment to run asynchronous code. And it's what Node adds on to what JavaScript offers as a language. The fact that Node uses JavaScript, which is a single-threaded language, may sound like a disadvantage, but it's actually one of Node's biggest strengths. It means that as a Node developer, you never have to worry about managing multiple threads, which simplifies how you write code. Node already knows who should do the work to get the job done. So as a developer, you don't have to think about it. It's only the code behind Node and the code behind your computer's operating system that internally has multiple threads and uses those threads to perform input and output tasks. It's these internals that allow Node to do its famous non-blocking I/O, that it's so famous for doing really well. And ultimately, this is what led us all here, to using Node in our applications and wanting to learn all about it. All right, until the next one, bye-bye. Welcome back. In this video, we're going to take a second, closer look at the event loop. This is one of the most important parts of the Node runtime. Why is it so important? The event loop is responsible for handling all those callback functions in your Node programs. Those callback functions which allow Node to execute code asynchronously. It's this event loop that allows your Node program to do multiple things all at once, even though JavaScript is a single-threaded language. So how exactly does the event loop work? What does it look like? When you start executing some program using the Node runtime, a piece of code starts running. This piece of code is a loop inside of libuv. That loop is called the event loop. You guessed it. This event loop, like every event loop, is a piece of code that looks something like this. We have a while loop that runs as long as some condition is true. For the event loop, it checks if the node process should exit, and if the process shouldn't exit, so say some flag should exit is false, our event loop calls a function to process events that have been sent to the event loop. Something like process events. So our loop checks if your code is done executing and the node process should exit, and if not, it processes all the events, all the callback functions that are called by your node program. If there's no events, the function here waits until there is one. It waits until your program triggers one of those callback functions, at which point it will execute that function, passing off any hard work to the operating system or to that thread pool. When it's done processing all the events that it currently has, it'll start all over again. That's it. This loop runs while Node is running and processes all the events happening in your Node programs. Now, the code you see here isn't exactly the event loop code that Node uses. The actual loop lives in libuv and is implemented in the C programming language, not in JavaScript. But it follows the same logic that we see here, processing all your asynchronous callbacks until Node is ready to exit, when there's no more code for Node to run. All right, now that we're aware what an event loop looks like, there's only one piece that's missing. How does the event loop process events? What does Node's process events function do? And what kinds of events does it actually handle? Let's find out in the next video. I'll see you soon. Welcome back. We now know that the event loop is a piece of code in libuv that processes asynchronous events. It handles our asynchronous code, going through any relevant asynchronous callback functions in a loop. Node automatically enters this loop when it starts executing your code, and it exits automatically when there are no more functions to perform. So what exactly happens when the event loop processes events? When Node executes an asynchronous function, say set timeout or our file system function to read a file on our machine, that operation is sent off to be executed in the background. As we've learned, this operation is executed in our operating system or on the thread pool. When that operation finishes and the result is ready, Node places any callback functions that it needs to run for that operation onto a queue. Say our asynchronous operation was this set timeout that waits for 1 second before attempting to call a callback that we're going to call callback1. What happens is that when this timer expires, when 1 second has passed, our callback is added to this queue to be executed as soon as possible. This is true for any callback that you've set to be run when some asynchronous operation completes. These callbacks are put on something called a callback queue. This callback queue keeps track of which callbacks are ready to be executed. Any new callback functions are pushed onto the queue in this order. So another set timeout that completes immediately after our first one would add its callback immediately after. And if we had a third operation complete with a third callback ready to execute, its callback might be added to the queue as well. So new callbacks are added in this direction from the bottom, and they're removed from the queue. They're executed from the top in this order, with callback 1 being executed before callback 2. This is what's known as a first in, first out queue. The first function to be put in, callback 1, is the first to be executed, because it was the first one to be pushed into that queue. This queue is like a waiting area for our callbacks, where the oldest function, the one that's been waiting longest, will be the one to get processed by our event loop first when it has a chance. We use this queue system so that all your callback functions get a fair chance to be executed in a reasonable amount of time without interrupting each other. There we go. I've probably said callback and queue a million times in the past couple minutes, but the next video is going to be a really good one. Let's find out exactly how the event loop uses this idea of a callback queue. Oh, and by the way, you may have heard the term event queue or message queue being thrown around in the context of the event loop. These are just different names that refer to the same thing. They all refer to this idea of a queue of callbacks. All right, on to the next video. Let's continue our investigation into how the event loop processes events. We've learned that when you pass a callback into a function, like setTimeout, when that timer completes, the callback gets put on something called a callback queue, or event queue, to be executed at a later time. Now, what does the event loop do with our queue of callbacks? Well, I'll let you in on a secret. There's no one callback queue. We do have queues of callbacks that keep track of which tasks need to be run, but if you look deep into the workings of the event loop, you'll see there's actually several different queues. Each one handles a different phase of the event loop. Whoa, what's this phase idea that I just introduced? Each phase of the event loop is responsible for different types of operations. There's 4 main phases of the event loop. Each of these stages is responsible for a different category of operations that the event loop processes. There's one for timers, one for input-output events, one for setImmediate, and one for close callbacks. Each of these phases has their own queue of callbacks that are executed during that phase. A callback for setTimeout would go on the timer queue, while a callback for a file system operation, well, that's input-output, so it would go on the I/O queue, which is responsible for all asynchronous input-output operations. This I/O queue is also known as the poll queue. We'll go through each of these phases in just a second. But before we get there, we need to understand this concept of timers. There's 3 types of timers that we have in Node. You might have seen some of these. We have set timeout, we have set interval, and we have set immediate. We've already seen set timeout in action, and set interval is very similar, except it sets a function to be executed many times repeatedly, with function calls separated by a minimum of the delay that you pass in as a parameter. Rather than executing your callback once, like set timeout, set interval loops that function on an interval. Set immediate is a special kind of timer. It sets the callback that you pass in to be executed as soon as possible on the event loop. In theory, this means it's going to be executed immediately. But the truth is, set immediate isn't so immediate. We'll really see this by visualizing the different phases of the event loop. Let's find out how the event loop flows through all of its different phases. When the event loop first starts executing, on the first iteration of our loop, the first phase starts getting processed. The event loop begins by going through all of our timer callbacks. These are callbacks that were passed into set timeout and set interval. The event loop goes through the timer's callback queue and checks if there's any functions for it to execute. Functions for timers that have completed. Once it's processed all of the functions in the timers phase, it moves on to the next phase. We're still in the first iteration of the event loop, or what we call the first tick of the event loop, and we're now dealing with all of our input-output callbacks. This is the majority of all your callbacks in a real-life Node application. It includes things like all your network and file operations, but basically anything that doesn't fit in the other phases goes here. So if your code is done reading a file, the callback for that read operation will be pushed onto the I/O phase callback queue, and it will be executed in this phase. Next up, we have the set immediate phase. Remember, set immediate is a special kind of timer, like set timeout and set interval, that instead executes after the I/O phase. As you can see, functions passed into set immediate actually execute after those passed into timers, like, for example, set timeout. It's called set immediate because it runs immediately after any I/O operations have finished executing, and before another cycle of the event loop starts. Before we move on to that next tick, there's one more phase, the close callbacks phase. This is for when you close a file or a network connection, and you have a callback that executes when that connection is closed. That's what goes in this last phase. When all of the close callbacks have been processed, the event loop cycle begins again. And it goes through this list of different functions that it needs to execute. So it first checks the timers, asking, are there any timer callback functions to execute? If yes, it runs them. And when it's done, it asks the I/O callback queue, are there any functions for me to execute? Does the callback queue for this phase have something for me to process? If not, or once it's done processing, it moves on to the next phase, and so on, until we start a new tick of that event loop. Now, there are a couple of other phases in the event loop, like the idle and prepare phase, but that's only used internally by Node. Our JavaScript can't do any operations there, so these phases aren't really important to us. The 4 phases we see here are those that really capture the behavior of the event loop and how it interacts with JavaScript. By going through all these different types of functions in the different queues, the event loop makes sure that all the functions that make up your asynchronous Node programs eventually execute. And that's it. Node combines this event loop along with the V8 engine and libuv to bring JavaScript to the server, allowing us to create all the websites and servers and applications that we can possibly imagine. Good stuff. I'll see you in the next one. As we're learning about the internals of Node, it's worth taking a step back and considering how is what we're learning about Node different than languages like PHP and Python. We've already seen that a crucial difference with Java, C, and C++ is that those languages support multi-threaded programming. But PHP and Python are both high-level, easy-to-use, single-threaded programming languages, just like JavaScript. So what's the difference? If we think back in the day, say 20 years ago, when it came to the web, PHP and Python followed a more traditional model, where they needed a web server, something like Apache, to handle multiple requests coming in. Apache was a big hit, and it had a lot going for it, including that it was free and open source. With this web server, any request to our server, say asking for some data, was blocking. So we would handle it in a new thread. Because each thread would be blocked by our blocking PHP or Python code, we would have to spawn another thread in Apache for the next request, and the next request after that, and so on and so on. Each client talking to our server would get its own thread, which means that our server needed a lot of threads, with a lot of resources being used by those threads. The server would only be able to handle as many connections as it could threads, which made building sites that serve millions of users quite difficult and expensive. Serving a site like Facebook or Google that gets a lot of traffic, your server would crash pretty quickly. In 2009, Node became popular because of its model of non-blocking I/O that we talked about. Taking in all of these requests, in the Node.js model, we take the request into the JavaScript engine. Remember that it's mostly single-threaded. And for each request coming in, we quickly pass it off from the engine to be handled by libuv, which queues it up on the event loop. Even though your JavaScript code runs in a single thread, Node allows you to handle thousands of concurrent requests by delegating or passing off the majority of the work. It passes this work off specifically to the multiple threads in the thread pool. And wherever possible, skipping over the thread pool and talking directly to your operating system. Because your operating system is already multi-threaded, this work can be done without blocking your server. All of this happens in the Node.js process. There's no need for an additional web server, like Apache, to create thousands of threads. Looking back on things, the PHP model worked pretty well. But for many connections at the same time, Node's I/O model worked really, really well. Now, looking forward, things these days are changing, and the concept of non-blocking input-output is being used more and more. Python, for example, has integrated support for running an event loop out of the box, bringing it a step closer to Node. However, none of these languages that we've talked about make it as easy to work with asynchronous programming as JavaScript in Node, because Node was built specifically to do asynchronous, non-blocking I/O really simply and efficiently. I know it sounds like an advertisement, but it's the truth. And we now have the tools to understand why. Just as a side note here, you can put a web server like Apache or the newer giant that's competing with Apache, Nginx, in front of a Node server. And it's actually a good idea to use them together sometimes if you have a larger, more complex application and you're going to be handling thousands of concurrent users. But it really depends on what you're building. We'll take a look at performance when we build our final project. But for now, let's dive into exactly when it's best to use Node. It's going to be a good one, so I'll see you there. Welcome back. So what is Node best at? When is using Node the right choice? Let's think about this in terms of what we've learned in this section. Remember this visual? How when your computer is reading from a file or making requests over the network, your CPU is spending a lot of time just lounging about, not working very hard. And it's your devices, like your hard drive and your network card, that are doing all of the work. We now have a more complete picture of this, where our Node code sends work to our operating system through the JavaScript engine and libuv, and it's our operating system which communicates at the lowest level to the CPU in what's called machine code. That's the actual language that your CPU speaks. And finally, as we saw before, the CPU will delegate certain tasks to your devices over a communication channel that's known as a bus. The point is that this whole system works but it's more optimized and faster in certain situations. Node is not particularly good at things like video processing or machine learning. These are blocking, processor-heavy computations. They block your CPU, or in the case of machine learning, sometimes your graphics card, or GPU. They're possible, but Node won't really give you many advantages over other languages and runtimes. What Node is really good at is servers and the many various things that servers do, like talking to databases and coordinating with many other servers and services on the web for things like emails and authentication. Node works really well when your main performance problem is input and output rather than heavy calculations. It works best when we can delegate these tasks to our operating system and the devices on our computer. If our code blocks in JavaScript, or we're using the CPU heavily, then our event loop will get stuck, and Node won't be able to manage the other tasks happening side by side efficiently. On the other hand, Node is really good at serving data for I/O-heavy applications, which just so happens to be most of what we do on the internet. For example, video streaming like Netflix is mainly input and output, sending video files from a database of videos through a server like Node and into a user's web browser, or a Netflix application. In fact, this is how Netflix actually works, using Node.js. Fortunately for us, the Node model aligns really well with how modern web applications are built. They take advantage of existing technologies like databases and various services on the web that we can put together to make something useful. Node is the glue that puts everything together. It was made for the modern web, which is why Node is doing so well. All right, let's keep going. I'll see you in the next one. Bye-bye. Now, there's one part of Node that we've been taking for granted a bit. And that's this idea that it's event-driven. We've discussed in detail the event loop, which is where our events get generated, asynchronously in the background. But what does this mean for us as Node developers? How do we react to all of the events from the event loop? The most universal way that you'll see in every programming language of dealing with events is what's called the observer design pattern. We'll talk about these design patterns throughout the course, but design patterns are proven approaches to solving problems that appear again and again in all kinds of different programs and applications. They allow us as developers to avoid reinventing the wheel, to avoid coming up with patterns of our own from scratch every time we encounter a new problem. Let's take a look specifically at the observer pattern, which is one of these approaches which we apply when we have something like, say, a celebrity. Say this mysterious racing driver. So someone famous who a bunch of people, their fans, are interested in getting updates about. These fans are observers. And the celebrity is the subject of being observed. So our observers subscribe to events from the celebrity that they're interested in to get notified when an event relevant to the subject occurs. Maybe our mysterious racing driver wins a big event, a big race. This event comes from the subject, who then notifies all of the observers. As long as the observer is subscribed to that subject, it gets all the updates from it. Now, each observer can react to that event in whichever way it needs. In this case, they all seem to be dressed in lab coats, so maybe they're doctors, and they just breathe a sigh of relief that the race ended safely. Whatever the observer and the subject are specifically doing, we tend to use this pattern when the subject that we're observing, our celebrity, doesn't just trigger one event, but instead creates a series of events that can be listened to by multiple observers and can occur spontaneously, more than once. So our race car driver can win a race on hopefully multiple occasions. Or they might start driving a new car. Whatever the event, there's a many-to-one relationship between observers and subjects. All that means is that just one subject can have many observers. So what's this useful for? Celebrities can be modeled using this pattern, but a button might be represented this way as well, with button hover and click events, for example. A database can be represented this way, with data being created, updated, and deleted on different collections of data. So each of those would correspond to a different event. And as we'll see later in this course, even different messages being sent over a chat client can be represented using the observer pattern. It's really so useful and is in fact the basis for popular front-end frameworks like React and Angular. And we'll definitely be using it in this course. All right, let's take this concept and explore how we might use the observer pattern specifically in Node. I'll see you in the next video.